So this chapter 5.3 is all about explaining how the horizontal asymptote is reached. So if this increased to 1,000,000 and this increased to 1,000,001, you essentially still got 1, but on the underside of 1, like because the bottom part is a little bit bigger than the top part. So that means as x approaches infinity from like 1,000,000, you're going to get just beneath 1, like 0.99999. Whereas this one, as we approach negative infinity, you're going to get negative 1,000,000 over negative 1,000,001. So we're going to approach 1, but on the tops, no, still on the bottom side. So you can see they both still approach y is equal to 1. One's on the both on the bottom side, slightly below 1, 0.99999. They're just trying to teach you why we use that equation instead of 3 over 2 now. For instance, if this approaches slightly below 3,000,000, this approaches slightly below 2,000,000, so it's going to be slightly below 3.5. So it's going to approach 3.5 from the bottom side. It's just teaching which side of the asymptote it's approaching when you see it logically. So if this approach is just short of 1,000,000 and this approach is just bigger than 3,000,000, it's going to be slightly smaller than 1 over 3. Then they teach you to measure things, figure out where y is on the left side of an asymptote, between the asymptote and the next asymptote, and on the right asymptote side of the asymptote. And what you do is you break down each factor and figure out if it be minus or plus, depending on, like below minus 4 over 3, let's say minus 2. So minus 2 is here's minus 4, so it's going to be minus. And then you keep doing that. If we pick 0 here, it's going to be minus. And if we hit pick 3 or anything above 2, it's going to be plus. Then it looks at each of them. And then when you realize, well, the top is dividing the bottom, so we have a minus dividing a minus, it comes out as plus. It's the top divided by the bottom. In this case, it's a minus divided by a plus. You get a minus. And a plus divided by plus is a plus. So they're teaching you how to break down what y will be, positive or negative, based on the individual factors in the equation. In this case, we're looking at x minus 2 over 3x minus 4. And that's really just, it's teaching you how to figure out where your graph will fall when it's a reciprocal, because reciprocals aren't, you can't really imagine the reciprocal in your head. So that's why they do it. So always look at your examples, because your examples will often be on tests. And any questions in the book will often be on tests. But they're just explaining how you'll find most reciprocal functions, and that these will both have a vertical and a horizontal asymptote. You can determine the vertical asymptote directly from the denominator. You can determine the equation of the horizontal directly from the function of the ratio of the top and the bottom. And then you can sketch them from that. So they're teaching you how to sketch these things. Okay, number 1, match the function with the graph. Now again, this is quite easy. You just have to focus on the simplest ones first. Okay, so let's just do this and then do this. Oh, that's a terrible image. Let me try to take a better image than that. Just zoom in here. Bit. Yeah, that's better. Let's try that one. There we go. Over there. And we'll do that. And there we go. That's better. Now look at this one over here. It's a line. So line, especially at 2, will be y is equal to 2. So we have to figure out which one of these could possibly end up in y is equal to 2. It won't be that one. It won't be that one. And there's a hole at x equals 2. So an x minus 2 at the bottom somewhere. We look carefully. This is the only one with x minus 2. Let's figure out how it becomes a hole. Well, if you look at the top, we can factor out a 2. We can factor out a 2. And when we factor out a 2 at the top, we're left with 2x minus 2 over x minus 2, which means those x minus 2's will cancel out, and we're left with y is equal to 2 with a hole at x is equal to 2, which is exactly what's going on here. So that means that this one is B. B right here. Just bring the B over. There we go. Now the other ones, we just look at the asymptotes. For instance, this asymptote here is at x about minus, looks like minus 2. It looks like it's coming over. So x plus 2 would be at the bottom. This is the only one with x plus 2. This one's, the asymptote looks to be roughly 1, so we should look at x minus 1 at the bottom. That would be that one. And that leaves that last one there. So let's just look at, well, let's make sure this one is not, looks like x minus 2.5. So that would be this one. So if you look carefully, the denominator, when we equal the denominator equals 0, you get minus 5 over 2, which is what this one is. Then, as I said, the only one with x minus, or at x minus 2 is this one. And the only one that's x minus 1 is this one. That one's x plus 2, rather. There you go. You can see matching them is not bad, especially as you start eliminating the easy ones. Okay, consider the function this. State the equation of the vertical asymptote. Use a table of values to determine the behavior functions near its vertical asymptote. State the equation of the horizontal asymptote. Use a table of values. Determine the domain and range. Determine the positive and negative intervals. Okay, sketch the graph. So that's the full deal. So if we look carefully, number 2 is right there. Drop it. And here we go. Sketch the graph. So let's figure this out. Well, first of all, it's got a number up top, which makes it a little easier. So when there's a number up top, the horizontal asymptote is going to be y is equal to 0. The vertical asymptote is right dictated there when we make that the bottom part equal to 0. So this, when we solve for x, was x is equal to 2. So that means the vertical asymptote is going to be x is equal to 2. So really, we just have to figure out what happens near these asymptotes. So what happens when this, at y, when this approaches positive million? Well, it becomes 3 over a million, essentially a very small number. So it's very close to 0. It's also going to be approaching 0 from the positive side. What about negative a million? Well, this becomes a very small number again, but negative. So it's approaching 0 from the negative side. So that means as we go to the left, it's going to be rising up to 0. And as we go to the right, it's going to be coming down to 0. And that is simply because one is positive and one is negative. So that's what a table of values would show. You can also just do it in this. Let's see if I can get to it. There we go. 3x minus 2. 3 divided by x minus 2. And we can just do a table of values down here. We can just copy this here. Put it down here and create a table of values. And we can make our values 0, or better yet, 3, 333, 3033, and just keep going, keep going. And then we can just make this x1. And then if this x1 and this f of x1. Still didn't do it. Let's try f of x1 here. Let's try putting this here. There we go. And we can see it gets to a really tiny number as we approach the far right. That's because it's a tiny number, but positive, because 3 over a million here is going to stay positive. Now let's look at the other side of it when we do minus 3. Minus 333, or minus 3, minus 3 million, and then a minus a huge number like that. We can see that we also become a very tiny number, but on the negative side, because it's just underneath the asymptote there. We can also see that it's true we have an asymptote at x is equal to 2 and at y is equal to 0. We just need to figure out what happens as it approaches the vertical asymptote. Well, okay, we got that. That's this one. So as we approach the vertical asymptote is 2. So what we would put is we'd start on the right side of it. What number is on the right side of 2? Well, 2.001 is good. So let's take 2.001 and put it in for x and subtract 2. And we get a really small number, 0.001. And when we take 3 and divide it by a really tiny number, we get a really huge number. And it's positive because it's positive here. And this is always positive, which means we're approaching, as we approach the vertical asymptote from the right side, we're approaching positive infinity, which almost means automatically the other side will be negative infinity. But let's take a number that's just to the left of 2. Number that's just to the left of 2 is 1.999999. When we subtract 2, we get negative 0.0001. When we take 3 and divide it by a negative number, we get a negative number, but we're also going to get a very big number, so we're going to get like negative a million, which means as we approach the vertical asymptote from the right side, we dive down to the negative million. And remember, we approach the horizontal um, asymptote from the bottom. So over here, it's going to be like that. So that almost automatically means we can draw our graph or sketch our graph. Domain and range is going to be XER, except X cannot be 2 for domain. And it's going to be YER, except Y cannot be 0 for range. The reason Y can never be 0 is simply because there's a 3 up here, and no matter what number we put in here, we're never going to get to 0. We're going to get close to 0, but we're never going to reach 0. So if I were to sketch it, it would look like this. There's my Cartesian. Then I'm going to put a X asymptote at 2 and a Y horizontal asymptote there. Since I know it approaches a really high number here and really close to the asymptote here, it's going to be like that. Something like that. And it's going to be almost, actually it's not going to be almost, it's going to be a perfect mirror from this side to the other side, diagonally. Let's see what else. Determine the domain and range, so it's XER, except X cannot be 2 because of the vertical asymptote here. And YER, except Y cannot be 0. Determine positive and negative intervals. Yeah, so to the right of the asymptote is positive. To the left of the asymptote is negative. And sketch the graph. There we go. You can even find a couple numbers in there. For instance, you could throw in 3. What happens when X is 3? Well, it becomes 3 over 1. So that means 3, 1. So you could even put a dot here, 3, 1 if you wanted. And what happens when it's minus 1? You get minus 3 over 3, you get negative 1. So at minus 1, you're going to get a negative 1. So there's a couple dots you could put in there. You could put in a 1 there. At 1, it's negative 3. So right there, that would be the opposite. At 1, negative 3. Yeah. And then when we go to our graph, sure enough, we can confirm all this. That's what's the great thing about these calculators. We can see that there's a 3, 3. Yeah. We can see that there's going to be a 1, negative 3. And there you go. And oh yeah, you can always find the y-intercept when x is 0. So if we make x is 0, we get 3 over minus 2, which is negative 1.5. At 0, you're going to get negative 1.5. So that's another point that's helpful to find is the x-intercept. Y-intercept. Simply make x 0. Okay, that's that one. They ask us to do it again for this. I'm not going to sketch it, but I will give some basics on it. And this one I'll just do really fast. So the vertical asymptote, we can see x plus 1 down here. So there's going to be a vertical asymptote. Let's just draw the graph. So there's going to be a vertical asymptote at x is minus 1 right there. And because the degrees are equal, x power 1, x power of 1, we take the coefficient 4 and divide by coefficient 1, which means there's going to be a y horizontal asymptote at y is equal to 4. And this x1 is x is equal to minus 1. And then all we have to do is find out what happens on the, we can make these numbers a million. And we discover, when it's a million, it's going to be approaching the asymptote on the positive side because they both become positive. And therefore, when it's negative a million, it's going to approach the asymptote from the bottom side, which pretty much automatically means it's going to be graphed like this. But to make sure, we're going to take a number that's just to the right of minus 1. We're going to take let's just take 0. So when it's 0, we get minus 3 over 1. Not quite what we want. 0 minus 3 over 1. Let's see, minus 3 over 1. Yeah. Oh, it looks like we're on the negative side. Hang on. So when I have 0, I get 4x times 0 minus 3 over 1. Oh, it's 0 kind of minus 3. It's down here. So I have to be careful now. I might have calculated wrong when I said that. Because if this is on this side, it's going to stay on this side. So let's see. Yeah. Let's see if what happens when we take a million again. I get 4 million minus 3 and 1 million plus 1. Oh, it's actually a number that's slightly below the curve. Sorry, it's positive, but it's because this is slightly more than a million and this is slightly less than 4 million. It's actually going to be on the bottom side of the floor. So there's a little calculation. Good thing I checked the y-intercept because that gave me a lot of information. As soon as the y-intercept's on that side, the graph pretty much has to be on that side. And the scale, of course, is not quite right. It could be something like that, but it doesn't matter. Doesn't matter. It's going to be closer to the asymptote, but it doesn't matter. Which automatically means on the left side, as I take negative a million, I get negative 4 million and 3, so it's negative 4 million and 3, and I get negative 1 million plus 1, which is negative 999,999, which means I'm approaching it from above. So there you go. And if I take a number that's just to the left of minus 1, like minus 1.1001, I get an infinitesimally small number down here. And it's negative. And I get a positive number up there. So yeah, I'm going to get going to infinity. So I'm not going to, you go ahead and do it and sketch it and take some numbers and figure it out. But that's the basic idea. It's the same idea as the last one. And then state the equation of the vertical asymptote of each function, then choose a strategy to determine how to graph the function as it approaches it. Okay, x is equal to minus 3, x is equal to 5, x is equal to a half, and x is equal to negative 1 over 4. Just set the denominator equal to 0 and solve for x. Oh, to figure out, to figure out what happens, take a number that's, for instance, if for this one, negative 3, take a number just to the right of negative 3, negative 2.99999. Take a number that's just to the left of negative 3, negative 3.00000. Plug it in 0.0000001. Plug it in the equation. You get 2 divided by an infinitesimally small number, so it's going to be approaching like 2 million if you divide by a smaller and smaller number, which means to the left of it is going to be negative, so it's going to approach negative a million. To the right of it is going to be positive, so it's going to be approaching positive a million. And that's what happens as it approaches. Do the same for all of them like that. Just take a number that's very close on the right side of the vertical asymptote and on the left and determine what your y is approaching. For each function, determine the domain, intercepts, asymptotes, and positive negative intervals. So let's start with the easiest thing. When x is 0, we get 3 over 5. When x is 0, we get 5 over minus 1, which is minus 5. When x is 0 here, we get 10 over minus 5, which is minus 2. And when x is 0 here, we get 2 over 10, or 1 over 5. So that's easy for when x is equal to 0. They're all numbers over top on this right side, so y is equal to here, 0 here. And over here, when y is 0, x is minus 5. When y is 0, x is minus 2. So you can figure out the y-intercepts across the y-intercepts both. That's because the horizontal asymptote here is 1 over 4, and the horizontal asymptote here is 1 over 5. So they're both above the x-axis, which means your graph will cross the x-axis. And decreasing, increasing, the same thing. Take the right of the vertical asymptote and to the left. Or just plot them into Desmos and understand what's going on. Read each set of conditions, then meet these conditions. These ones are crazy. Okay. 6. Okay, if I want to create something that has a vertical asymptote but minus 2, I have to have an x plus 2 in the denominator. That's all there is to it. If I want to have a horizontal asymptote y is equal to 0, then I just put a 1. We want it negative when x is going down to, when x is minus this, and to the right of the asymptote, or to the left of the asymptote, we want the whole thing to be negative, and we want it to be positive when it's over here. So let's see what happens when it's negative. Yeah, it's a negative number. And when it's a big positive number, yeah, it's a big positive number, very tiny, and it's approaching the vertical asymptote, which is 0. So essentially we have, when it's like that, and like that. Oh, where's minus 2? Over here. So it's like this, right around the asymptotes. Vertical asymptote at x minus 2, so the same thing. Horizontal asymptote at y is equal to 1. Okay, just put an x up there. We're set. X-intercept 0, y-intercept 0. Okay, 0, 0, I guess is what they're saying. When x is 0 here, we get 0 over 2, which is 0. So that's good. And we want it positive when x is going to negative infinity, and we want it negative when it's this. So we're just going to put a negative number here. And that will flip the whole graph when I put a negative. That means when I take negative infinity here and negative infinity here, this becomes positive, this becomes negative, so the whole thing will be negative. When this is a positive million, and this is a positive million because of this negative, we're going to get a negative number as well. Well, let me make sure that. So when this is negative, this becomes positive. When this is negative, it stays negative. It's a negative number. When this is positive, that stays positive, or that goes negative, and that becomes positive. Both are negative. Hang on. Negative, this becomes positive. Negative, this stays negative. So actually, in this case, it stays on the underside. That shouldn't be, though. Let's see. Positive when we go to the left. So if I take negative a million x, just get rid of it. I want it to be positive, so if I take a million x, and negative when it's to the right, no, that doesn't work either. They're both positive. Now let's just take a number just to the left of the asymptote. Let's take, so the asymptote's at minus 2. Let's take negative 3. When we get negative 3, we got a negative 1 down here, negative 3 up here, and we're talking positive 3. So that means this works fine for positive numbers to the left of the asymptote. Okay, let's take something just to the right of the asymptote. Let's take 3, or sorry, negative 2, so negative 1. Negative 1 plus 2 is 1, and then negative 1 up here. Therefore, we got a negative number. So yeah, this works the way it is, like that. And let's just make sure. Yeah, positive on the left of the asymptote, negative on the right of the asymptote. Up to the horizontal, anyway. All right, let's see the rest. Pole at x equal to plus 3, so you get x minus 3 on the bottom and x minus 3 on the top. No vertical asymptote. Yeah, so just like that. At the y-intercept, we have that. Okay? Actually, that's an interesting one. Let's do C. We got C here anyway. Okay. To get a hole at x is equal to minus x equal to 3, we need an x minus 3 at the bottom and x minus 3 at the top. Now this would create a horizontal asymptote at y is equal to 0. They don't care if there's a horizontal asymptote or not. How do we get it when x is 0 to 0.5? Because if we look at x is 0 like this, it becomes minus 3 over minus 3 which is equal to 1, which means we should have a 2 in front of this. That way when x is 0, we get 2 times minus 3, minus 6, and when x is 0, we get minus 3. So we get minus 3 over minus 6, which makes a positive half, which is that. So let's see if that's true. X minus 3 over 2 times x minus 3. Okay. And let's determine what happens when what f0 is. There we go, it's 0.5. That's the easiest way to go do it anyway. There we go. You could make it even fancier, but they don't want an asymptote, so it doesn't really matter. This is the fastest, easiest way to do that. And why complicate your life? Vertical asymptote here, when and x equals 6, so there's 2 factors in the bottom. Horizontal asymptote y is equal to 0, so we put a number. Positive to the left of minus 2, or to the right of 6, and negative when in between them. Increasing from negative infinity to 2, decreasing from 2 to negative infinity. Yeah, I mean, it's not that hard. Let's just work with the asymptotes. Okay, so we got x plus 2 and x minus 6. Like this. There we go. Negative on the bottom, positive on the top, increasing as we go this way, decreasing as we go this way. There you go. It happened just naturally. Now, sometimes they want the other direction. All you have to do is put a minus. A minus will flip it vertically through the x-axis, mirror it through the x-axis. So if they said they wanted positive from minus 2 to 6, and negative to the left of minus 2 and to the right of 6, that's what you'd do. Flip it. And just take samples in between. Like the best sample in between these two is 0. You just plug in a 0 here and you get 2 and minus 6. 2 times minus 6 is minus 12. You get minus 1 over minus 12, which is positive. So it would be positive. If we didn't do anything, that would be negative. So it would tell us right there at 0, we're going to get 1 over negative 12, which is negative 0.083. Use a graphing calculator to discover the similarities when n goes from 1, 2, 4, and 8. What will happen is the asymptote will go from y is equal to 8, y is equal to 4, y is equal to 2, and y is equal to 1. As the thing approaches infinity, the asymptote will approach y is equal to 0. And as f is negative, it's just y is equal to minus 8, y is equal to minus 4, y is equal to minus 2, y is equal to minus 1, and as it approaches negative infinity, it will approach y is equal to 0 from the negative side. So just to demonstrate that, x over x and x plus 2. So you can even write it like that, x over k x plus 2. And then we just use a slider for k, and we just say what happens when k is 8. 8. And I can even put in a formula here. Oh yeah, it had 8x up here, didn't it? So we'll start with k is equal to 1. And I can even use my asymptote as 8 divided by k. And I can draw it. There we go. It'll draw it with me. Now what happens when k is 2? The horizontal asymptote goes down to y is equal to 4. Right there, you can see it right there. When k is equal to 4, the horizontal asymptote will go down to y is equal to 2. You can see it right there. And finally, when k is 8, the horizontal asymptote will go down to minus or positive 1. Y is equal to 1 right there. And all that will happen on the negative side of it is it'll go on the negative side, negative 8, -4, -2, -1. It's the same thing just on the bottom. And then finally, they want to ask what happens when this approaches -1,000,000. Well, my horizontal asymptote will approach just on the underside of 0. What happens when it's positive 1,000,000? Same thing, except it's going to approach y is equal to 0 from the positive side, which is what we predicted. Without using graph calculator, compare these graphs. So this has a horizontal asymptote of 3. This has a horizontal asymptote of 1 over 2. This has a vertical asymptote at x is equal to 1. This has a vertical asymptote at -3 over 2. That's about it. They're not that similar. Then they give us this. Well, that's fair enough. Let's do this. It's a practical example. There we go. Oh, didn't get it. Let's try it again. And we're at 9 here. I'll take 10 as well. Okay, so what happens? The value of investment in thousands of dollars, which means we add 1,000, multiplied by our answer by 1,000, when the investment after 2 years. Well, for 2 years, for time is equal to t2, we would simply put a 2 wherever we see t. So 2 here, and we're actually looking finding investment of 2 years like that, and 2. So 2 times 15 is 30, plus 25 is 55 over 2, which is roughly 27.5, and then when we multiply it by 1,000, $27,500 is our investment. And then you do the same for 1. When we plug in a 1 here, we get 15 plus 25 over 1. 15 plus 25 is 40 over 1. So our investment is higher after 1 year. So that means this investment is going down. What is the value of investment after 6 months? 6 months is 0.5 years. 0.5 years, so 15 becomes 7.5 plus 25, 32.5. And when it's divided by 0.5, it doubles, so $65,000. The investment's clearly going like that. There's an asymptote in this graph, function t is equal to this. Does this make sense? Play why and why not? Yes, because at time is equal to 0, nothing's happened with the investment, so it doesn't matter if there's an asymptote there. It also wouldn't matter if there's an asymptote to the left of time of -1, because we don't have such a thing as negative time. Choose a very small value of t, calculate the value of the investment. Do you think that function is accurate this time? Probably not. We're probably going to get like millions of dollars, and really, it's not practical. So if I take a tiny value of t, this becomes nothing. So I get 25 over like 0.000001. So it's going to be like 25 million. The investment will be huge as we approach time is equal to 0. Not realistic, because how in the hell could, after 0.000001 seconds, could I make $25 million? Number 10. An amount of chlorine is added to a swimming pool. The concentration of chlorine is C at a certain time t, where C is measured in milligrams per liter. What happens to concentration of chlorine during the 24-hour periods after the chlorine is added? Well, let's get an idea of what this graph looks like. Let's just graph it first. Here it is. What's the vertical asymptote going to be? Well, solve for t down here when it's equal to 0. T is equal to -2. So that means at a very odd, impossible -2 seconds, we have a vertical asymptote. How about horizontal? Yeah, well, keep in mind that this t over here has a 1 in front of it. And really, we should switch the places of these numbers. But because there's a 2 here and a 1 here, the horizontal asymptote is at y is equal to 2. Okay, so now that we have that, let's figure out what happens at time 0. At time 0, this numerator becomes 0, so the whole thing becomes 0, so we get 0, 0. Now we know what side of the graph it's on. We can perfectly guess that it's going to hug the asymptote, because that's the only place it can go is towards the asymptote. So we can just take a value of 24 for t. When 24 hours, we get 48 up top, divided by 26. And you can see we're almost at 2, but not quite. So after 24 hours, it's reaching that. So essentially, we're going to have something like this. There you go. The key characteristics. Geez, we could just put this into decimals. That'll be easier. And then you can set your variables. And just say, oh, so when it's all 1, right, you really can't see a graph at all. It would be x plus 1, which is going to cancel out and form a solid line at 2. And you're going to see a hole at somewhere along here, on the other side. There we go. And let's just increase the a's to 5 and this to 5 and see what happens. Same problem. Let's make the c slightly different. That changes the asymptote. Actually, let's just hit play on all of them and see what happens. So both the vertical and the horizontal asymptotes change. Keep in mind, it doesn't have to go from -10 to 10. It could be infinite numbers. So let's actually do a -1,000 to 1,000. We'll do it for all of them. The other one's still running. All right, let's just start by clicking one of them. So this is the A value in front. You can see the A value is sort of, let's pick a spot there. Let's pick a spot that's reasonable. Yeah, get a bit better picture of this like this. So it's sort of going down. The asymptote is changing depending on what the A value is because it's getting much bigger than all the other ones, which makes sense. Same thing will happen with C. Probably happening a little too fast. Yeah. There we go. Yeah, see, it's just affecting the asymptote, and it's really only affecting it when we're near 0. That's when we can see it the most. When it's 1. There we go. That's when it starts becoming a possible curve. Anyway, let's see what happens when we change the B. The B is the number that's being added at the end. You can just see that it's kind of just squeezing closer and closer to its symmetry point as B approaches -0 or negative numbers, or the whatever the value of A is, which is 110. Let's put A back at 1. Yeah, there you go. It's approaching the symmetry point, and the same thing's going to happen when we hit D. Oh yes, of course, because D is the vertical asymptote dictator more. You're going to see the vertical asymptote shift left and right. So you can see as we shift A or C, the horizontal asymptote shifts. When we shift B or D, actually just D, the vertical asymptote shifts, and B will just affect the x-intercept. All right, not all asymptotes are horizontal or vertical. Find a rational fraction that is neither horizontal or vertical. Okay, that's just making the degree on top higher. Get rid of these. So if we have 3x squared cubed, let's say plus 2, and we divide it by, let's say, 2x squared, we'll get what we want. Goes tearing off to the top, but ultimately we're going to get the equation. How do I get 2? How does 2 become 3? It becomes 3 by multiplying it by 3 over 2x. There we go. There's the formula for the vertical asymptote. I essentially divided the top by the bottom, long division. There. Not hard. Use long division to rewrite this in the form of this. Okay. What does it tell you about the end behavior function? Fair enough. Let's do that. That's a good practice. 13. Okay. Oh, yeah, let's take it from over here. Crop, like that. Didn't crop it very well. There we go. Let's crop it like that. Okay, if I take this and divide it by that, so it goes in 2x times. When I multiply x, let's make that a little higher, it goes in 2x times. When I multiply x minus 1 by 2x, I get 2x cubed minus 2x. Oh, it's 2x squared. How many times it goes in? Minus 2x squared. When I subtract that, this negative 2x squared becomes positive, so it becomes negative 5x squared. Minus 7x squared plus 2x, long division. To get this to 5x, negative 5x squared, I have to multiply it by minus 5x. When I do that, let's give myself a little bit more room. I get minus 5x squared. And the next thing becomes positive 5x. I bring down the plus 8x here, like long division, you bring down the next number. When I subtract these things cancel. By the way, these things cancel here. And I get 8x minus 5x, 3x. To create a 3x here, I have to multiply it by 3. I have to bring down the minus 5. When I multiply the 3 times the x, I get 3x minus 3. When I subtract them, I'm left with minus 2. That's my remainder. Now, how do you write this? This is how you write this. You write it as y is equal to 2x squared, in brackets, 2x squared minus 5x plus 3, and then the remainder is a minus 2 over x minus 1. Let's see if that works. So we're going to start with the first main equation. The first main equation was this. The whole point is to make them look the same. And then it looks like this. So it's, it's a cube. And remember that it's all over, I'm going to do this, x minus 1. So it looks like that. Now, the whole goal is to make sure that this one, which is the remainder that we got, like this, minus, oh, gotta get rid of that multiplication, minus the remainder which was minus 2 over the original divisor. There you go. This graph is the same as the red graph. And that's simply because this is the quotient. I think that's the quotient it's called at the top. And this is the remainder, and you always put the remainder over the original divisor, which is that. So it's essentially when we divide this into that, we get this as this remainder, and it will be the same graph. And you might ask, well, how would we go backwards? Well, we'd have to put them over the same denominator, which means we have to multiply this top and bottom by x minus 1, and that's how it will become the original graph above. So this essentially only has a denominator of 1 right now. You'd have to create it as an x minus 1 to get it back into this form. What does that say about this last part? Well, this over here will dictate how much the graph goes up and down. So when x is a million, the graph won't go down at all. But when x is really, really, really tiny, or really, really close to 1, the y-intercept will go up huge. So I'll give you an example. When x is 1.001, it's going to go down. That's going to be the horizontal asymptote. Or I won't say the horizontal asymptote. That's where it's going to end up. It's going to be lowered down to there. This will have an oblique asymptote, which will happen to match this formula, which is the remainder. See? Even the remainder can be a parabola and still match the asymptote of this function, which is fascinating, actually. So there you go. Fiddle with the graphing calculator. It's a great way to learn. Let this equal to this, and this equal to this, and this equal to that, and this equal to that. Which of these rational functions has a horizontal asymptote? Okay, this one does, this one does not, this one does not, and this one does. So this one's going to be y is equal to 1, and this one up here is going to be y is equal to 0. Which has an oblique asymptote? This one, because the degree is bigger than the bottom, and this one, because the degree is bigger than the bottom. Which has no vertical asymptote. No vertical. So this, when we set it to equal 4, has a vertical asymptote of 2 and minus 2. This one we'd have to solve. It looks like it's x minus 2x plus 1. No. X minus 3x plus 1. Yeah. So that has 2 vertical asymptotes. This one cannot solve. This will stay positive, this whole graph. So it will not have a vertical asymptote. It'll be a bump. And this has a vertical asymptote of x minus 2. So this is the only one. What does that look like? X cubed plus 8, x squared plus 9. Looks like that. I shouldn't say it's going to stay positive. I should just say it doesn't have an asymptote, the vertical asymptote, because there's no way to make this equal to 0 and solve. It'll, once we hit around 3, actually around 0, it will switch down to the other side. And graph y is equal to mx, showing the asymptotes and intercepts. Y is equal to mx. Oof. Well, you can do that. And there, that's the end of 5 point, what was that section? 5.3.